We've given lots of information here, but the main of it is shown in the diagram. Let's just check anyway. So we've got these two small balls. We're kind of assuming they're little particles. It's always worth thinking about what modeling assumptions you're making as you go along. 3 kilograms and 2 kilograms. Now I'm tempted to just straight away write on the weights because, the forces is what we're interested in. Surprised that's not filled in because normally forces are shown with filled arrows. This is going to be 3g, where g is 9.8, um, my gravity constant. So, and then over here, or hold on, I'm going to show all the forces on P in blue, and then the forces on Q in red. This is going to be 2G. We've got the string held at rest on a rough horizontal surface, so there's some sort of friction going on. The string passes over a pulley as shown, which is fixed at the end of the surface. Q hangs vertically below at a height of 2 meters above a horizontal floor. So the first thing you should do is like basically, draw. We might not have been given the diagram, but we are here, but draw it yourself and then add some of these things on. The system is initially at rest and a horizontal force of magnitude 40 newtons acts on P as shown. Before I read any more, let's just add on anything else. So because this is on a surface, it also has a normal reaction force, and it's actually going to be exactly the same. So I would be tempted to just write that in. R P is also equal to 3G. There's no other forces helping us. I mean, if it was, we'd have to change it later on, but there isn't in this question. There is no normal reaction applied to Q because it's actually suspended in midair, but what is keeping it there? It's the string. So we introduce this tension, T. And the result is that this is actually pulling the blue particle to the right, or trying to, and therefore the tension here is acting to the right, and it'll be exactly the same. So that is our setup. One thing we've not said yet is that P is now released and moves directly away from the pulley. Okay, once it's been released, a constant frictional force of magnitude 8 newtons opposes the motion. So the motion is going this way and this way, therefore. So because it opposes the motion, I've got this other 8 Newton force, which I'm just going to add here. Nice. The balls are modeled as particles, the pulleys modeled as being small and smooth. These are all things we need to be able to deal with this question in a simpler way as possible. The strings modeled as being light and inextensible. Show the magnitude of the acceleration of each particle is 2.48 meters per second squared. Now, because they're connected and the string is not stretching, what that means is that the acceleration this way and this way are going to be exactly the same. So let's take a look at, first of all, Q is slightly simpler. So apply F equals MA up. T minus 2G is therefore going to equal 2A. And then for P, you're going to apply F equals MA to the left. I think it is good to say exactly what you're doing. Sometimes you resolve forces because they're equal and they cancel and everything. But we should quote the formula that we're actually using, and the direction that we're applying is positive. That's what I mean by up. I'm saying that up is positive, and then to the left is also positive. We can swap it around later on. We just have to be careful because it will change the equation slightly, just with negatives and so on. So here I've got 40. Now I'm applying it to the left, so actually the weights don't come in and the reaction force don't come into this. 40 minus 8 minus t is going to equal 3a. And we've got simultaneous equations to solve. So I'm just trying to work out where I should do these. First of all, this will change to 32 minus t is equal to 3a. This is actually a very standard set of simultaneous equations for connected particles. You end up with one of them with a plus t in it and one of them with a minus t in it. So what we can do actually is just add the two together very quickly to get rid of t, because we're being asked for the acceleration. So adding will give, these will cancel. I'm going to be left with 32 minus 2g is equal to 5a. And therefore a is going to be 32 minus 19.6, because that's what 2 times 9.8 is, divided by 5, and we're hoping to get 2.48. You could always just put in the 2 times 9.8 to be fair. Hey, brilliant. So I know I've squashed it in a little bit, but it's just so you could see the diagram at the same time. So dealt with that bit. Then asked to find the tension in the string. So we've worked out, actually remember, we've got simultaneous equations, so we're just substituting in back in, basically. And I could put it back into either one. Arguably, this one I've already got plus t in it, so I'm going to use that. So t is going to be 2a plus 2g. So it's going to be 2 times 2.48 plus 2 times 9.8. So I didn't write it in exactly the same order, but it's the same thing. 24.56 newtons. I'm going to write that, but then we are often asked to round to three significant figures because we can't actually be that, we can't be that accurate. So I'm going to write 24.6 newtons as my final answer. All right, and that followed on quite easily from having calculated the acceleration. And the nice thing is, because this is a show that question, even if you couldn't do this first part, you can still do some of the later parts. If you struggle with the forces part. Next up, we've got some motion going on. And this motion involves, so when the balls have been in motion for 0.5 seconds, the string breaks. So it's going to involve Q traveling up for 0.5 seconds with this resultant force of T minus 2G. And then when it breaks, that tension completely disappears and it's a free falling particle. It's still moving up for a little bit, but then it's going to come back down, and therefore asked to find the additional time that elapses until Q hits the floor. So we've got a constant acceleration. We're going to be dealing with Suvat equations. Okay, so consider Q. And actually I'm going to say between t equals 0 and 0.5. It's being pulled up. So we want to know basically as much as we can about what's happening when it's like at the point, at the 0.5 point. So I'm going to apply Suvat, and I'm going to say that up is positive. So A, because the acceleration is positive here, A is equal to 2.48. Remember, U is equal to 0 because it was let go when it was at rest. And now the time duration is 0.5 seconds. So I can use V equals U plus AT to calculate the final velocity. And that's just going to be 0 plus a half of 2.48. So it's going to be 1.24. Okay, so that's quite useful. It will be. And S, I can use S. I can use any of them now, basically, that involves S. S equals ut plus half at squared seems a good shout. So u is 0, so it's just going to be a half times 2.48 times 0.5 squared. Which gives 0.31. So it's moved up 0.31 meters in that time. So now consider, sorry, so now string breaks. Consider the time between this and it hitting the floor. I'm going to apply suvat this time down. And just to tell you, I've got this particle here. There's no string involved. It's moving up. We've got a floor here. We know at this point, actually, because it's moved up by 0.31 meters, it's actually going to be 2.31 meters from the floor. Because don't forget, right at the start of the question, it was 2 meters above. Okay, these are things you have to realize. And then the original velocity now is going to be this 1.24. Okay, I just thought a little diagram would help, but let's actually get it written down as before. So A is going to be 9.8, like it's now operating under gravity. U is actually minus 1.24 because I'm applying suvat down. So I know I wrote it there as 1.24, but that was the speed. And then S is going to be 2.31. So we needed this information here that now goes into this. And I've got that S is 2.31 because I'm interested in now it traveling that distance to the floor. So I want to find T. I've got U and A. It's going to be another case of using S equals UT plus a half AT squared. You can actually alternatively find V, and then so V squared equals U squared plus 2AS, and then use that to help find T, because you could use V is equal to U plus AT after that, or one of the other ones. But I'm going to avoid finding V. We're not asked for it, so I'm going to go straight into it. 2.31 is equal to minus 1.24 T plus 4.9, because that's half of 9.8 times T squared. Okay, and it's fine actually to just use the quadratic formula on the class with calculator to sort this out. We don't need to do any calculations. This is a question that's testing us on suvat. Yes, we have to realize we have to solve a quadratic, but we don't have to show lots of working. These are awkward numbers. So there's an equation function, polynomial. Just type in the coefficients. Okay, so we get 0.8246. Probably just say that we're using the quadratic formula. Now, there's typically two solutions to a quadratic, and the second one is minus 0.5716, which is negative, so we're going to reject on a physical basis. Don't think we need to even write, maybe I should just write that t is greater than 0. And therefore, to three significant figures, t is going to equal 0.825 seconds. Now, the other way you could have done this question, it's more complicated, but sometimes I see people do it, is you could work out the time that it takes the particle to stop momentarily, i.e. when v is equal to 0, and then do a Suvat equation, a second lot of ones where it has to then fall to the ground. It's more complicated, but it does work, so I'm not going to show it here. Okay, actually in D, we are asked for the speed of Q as it hits the floor. So if I had worked V out first, then and substituted in for S, it would have been similar amounts of effort because I've now got to do it anyway. Sorry, in this one, I should have said. We actually don't need to get the time correct because we can just use V squared equals U squared plus 2AS on this. I'm assuming you know your Suvat equations or using them from the formula book. I'm just quoting them very quickly here. Okay, I think this was sorry, part D, I believe. So v squared is equal to u squared plus 2as, which is going to be minus 1.24 squared plus 2 times 9.8 times 2.31. Because we're squaring a negative, we actually don't even need to include the negative sign because it will cancel out. So 1.24 squared plus this gives 46.81. Now we're only interested in the speed, in fact. So I just need to take the positive solution. 6.842. Maybe I should write plus or minus. So the speed is going to be 6.84 meters per second. You get away with not writing the unit in these sorts of questions, but it's always good practice to write it down. So that's why I'm doing that. Okay, E. Write down the magnitude of the normal reaction force acting on Q when Q has come to rest on the floor. Well, actually, it's going to be exactly the same as it was right at the start of the problem. I even wrote it down. So it's going to be the same as the weight. And it's only 1 mark, so I don't think we need to write much. Just that it's going to be, maybe I'll draw a little diagram. So I've got 2G acting down, RQ acting up. RQ is going to equal 2G, which is going to be 19.6 newtons. And finally, F. State one improvement that could be made to the model. Hopefully you've talked about that we are modeling a situation here. It's not exact. We're doing mechanics, and there's different levels of complexity, and this is actually the simplest one pretty much. So I always go with air resistance. I say we could include air resistance in the problem. That's always going to slow things down. Just a few other answers from the mark scheme are a more accurate value for G, variable resistance rather than a constant, I think that's talking about the friction, potentially, is it? Include the dimension of the pulley so that the string is not parallel to the table. Include a frictional force at the pulley. Okay, these are all just things that you could write about. These are just examples, so as long as you've put one in that, I'm not going to go through all the other possibilities. I just think air resistance is a good one, but yeah, that's it for this very last bit.